We need more evidence, but this is certainly a starting point. That's the simple way to get the density. However, more commonly, it's done faster in this way. What we do is we find the density of a liquid in which the glass starts to float. I don't know what this liquid's going to be. Maybe some kind of an oil, because glass generally does not float on water. But let's say some kind of an oil. Then we heat that oil, or add whatever we do. We change the density of the liquid it's in by adding another liquid. Let's say the glass sinks, right? The glass sinks. So what that means is that the glass is of higher density than the liquid it's in. So what we do is we add a more dense liquid to the liquid that it's in, that mixes with the liquid that it's in, that will raise when this mix that will raise the density of the liquid it's in. Keep on adding this other more dense liquid until we get to a point at which the liquid the glass is in is so dense it's equal to the density of the glass, and the glass will start to float. So if we know the density of the two liquids and the amounts of the two liquids, then we know the density of the mixture of the liquids. And since the glass is floating at exactly this density, we know the density of the glass. That is the more common way of finding the density. It's done by machines, by the way, or by devices that will do this by itself. So it's more a little bit faster, and that's why it's more commonly done this way, with adding the more dense material until the glass floats. Finding the refractive index. Well, what you can do is send a laser right through it, but that's really inconvenient. They test glass, by the way, more commonly with refractive index than density. But again, good to have both. That's a positive way of knowing exactly what kind of glass this is. But anyway, refractive index is not tested by sending a light beam through it, but what you do is you put it in a liquid, let's say water, common enough. We know exactly what the refractive index of water is. Now, if you put it in water and then the glass has a different refractive index of water, it's going to have a glow at the edge of it. You've probably seen this for yourself if you ever put glass in water. Again, it's got to be lit up. I mean, it doesn't do it in the dark. So you shine light on it, obviously, and you'll see a glow around it, a white glow, because of the way the water and the glass have a different refractive index. Incidentally, if you put one liquid into another liquid, you might see little swirls if you look carefully. That's because the two liquids have different refractive indices, and the way the light's going through it is like bending where the liquids are mixing. Eventually, the liquids mix entirely, but again, you can sometimes see it. Anyway, you put the glass in water, let's say, and you shine a light on it, you'll see a glow around it, because that's where the refractive index changes. What you do then, is you heat up the water, so you change the refractive index. So you heat it up just enough to change the refractive index of water so that this glow will disappear. When the glow disappears, that means it has the exact refractive index of the fluid it's in, of the water it's in. And since we know the refractive index of water at all these temperatures, we'll know the refractive index of the glass. See? Again, we put the line, by the way, the glow around is called a Becke line. So we put the glass in water, let's say it looks like this. We'll, let's say, heat it up. And if we heat it up just enough to make the line disappear, we'll know the refractive index of water, and we'll know the refractive index. Oh, it's not that, by the way, it's not necessarily water. It's probably a different liquid. But I'm just giving you water as an example. So anyway, so we heat it up enough, we will get a point at which the line will disappear. That's where the glass will have the exact refractive index as the liquid. And we know the refractive index of the liquid at that temperature, so we'll know the refractive index of the glass. In fact, if you're looking at the glass, it'll actually seem to disappear. Because without that glow, it's very hard to tell to a solid and a liquid that have the same exact refractive index. If you heat it up, let's say, too much, you'll actually get the refractive index to go the other way. Now, that way, the refractive index of the outside will be lower than the glass. Let's say it's higher than the glass when it shows this. Whatever it might be. I'm not even thinking of which higher or lower. But let's assume it's higher when the glow is outside. You heat it up enough that the glow will actually get inside, where it gets lower than the glass. But the point is, you can find where it gets exactly the same as the glass, the liquid, and since we know the liquid, we'll know the glass too. That's how we measure the refractive index. There are machines, by the way, that do this. That home in on this beak line, they change the temperature, and where the beak line disappears, they stop right there and say, oh, now I know the refractive index. It's done by their machines that do that. So we have these class characteristics of refractive index and density. When they are both the same, both refractive index and density are the same for in the suspect glass and the crime scene glass. Okay, we can again make some kind of connection. Or if we have glass found in, let's say, a criminal hideout, and we don't know where it came from, we can narrow down the sources of where it came from by getting the refractive index and density. We see, let's say, the company that makes glass of this refractive index and density, and we'll see what are the customers of this company. So we can, again, get a lot of information out of glass. And again, glass is found everywhere. The FBI has a database of different kinds of glass samples, densities, refractive indices. That's what we want. So we can match it up with this database. If we have an unknown piece of glass, we don't know where it came from. Well, get the refractive index and the density, matched up with something in the FBI's database, and see who makes the stuff. And the database doesn't only say relate this glass to this density and refractive index. It actually provides a probability of all the glass makers. And if this is this glass is almost nobody makes this kind of glass, it'll give a probability of finding this glass anywhere else. Because if no one else makes it, it'll be a very low probability, which makes it have more evidential value. If it's a probability that lots of people make this kind of glass, then there's a low probability. Then there's a high probability of finding it elsewhere. So it would have less evidential value, because if everyone has it, finding it let's say in the suspect's area will not enable you to find out where the suspect was earlier, because this stuff is found all over the place. You can find many places. But again, if it's a rare kind of glass, then you might be able to say, hey, it's in the suspect's area. Where did the suspect pick it up? Suspect must have been in a certain place which had this glass. So again, these are things that help with the crime scene investigation. To get individual characteristics from glass, it's not being done that much now. The technique is possible. It is done in laboratories, at least. It does not have common use yet. It's laser ablation. That's when a laser hits the glass. We're not going to talk about it much. The laser hits the glass, and it has such a powerful beam, it'll actually evaporate the glass material as a gas. The gas goes through what we call a gas chromatography column, which will separate all the different parts of this gas, this glass gas, and we can identify trace elements when we put that through a mass spectrometer. We're not talking about these things yet. We will get to them soon, hopefully. What a gas chromatography column is and what mass spectroscopy is. But the point is that when the gas goes through this column, it's separated into the elements that we can find, and we can identify them using this mass spectrometer. So every batch of glass can have a different trace element, and the way to get it is to hit it with a laser, send the thing through this column, and identify it with this spectrometer. It's not in common usage, but it certainly can do this. Other information you get from glass comes from the way it breaks. And again, violent crimes and glass, they cause broken glass, right? So how does the glass break, and what information can we get out of that?